Yeah, it's been a blast being here. Thanks again to Monash and Osgrav and also Swinburne for hosting me. This is just first stop of several on my sabbatical trip, but it's going to be hard to beat Melbourne in Australia. It's been really great here. So yes, first let me highlight this animation inspired tangentially by the Kepler orrery of our catalog of binary black hole mergers. This visualization tool was written by Zohair Doctor, who was a postdoc in my group, and is now research faculty at Northwestern. This is just visualizing the binary black holes in our latest catalog, and is a pretty fun visualization of where we've gotten in a relatively short period of time. Good. So let me make sure we've got. Good. Slides are available online. Feel free to snag this QR code, and it actually renders pretty well on mobile. So you can also go back to this later on my website and grab the slides if you want to. If you wanted to look back and ask me any questions about anything, it'll be useful. I'll leave it up for a second. But today I'm going to talk about kind of a range of things, and some of you have heard various pieces of this from, I've spoken on the Compass call, I've spoken at the Osgrav retreat. So apologies if you do see some of these slides for a second time, but don't hesitate to interrupt me at any point along the way. Ask me loads of questions. I'd love to not get through all my slides. Good. So quickly, let me just highlight my group at University of Oregon, who does a lot of this work that I'm going to talk about today. Bruce Edelman was my first grad student. He has since defended and is now working actually in DNA statistics at a lab at the University of Oregon, using a lot of the same tools that we use for gravitational wave populations, but instead looking at human populations. J.D. Merritt was actually out here visiting Monash about a year ago, doing some, most recently, some work on stellar evolution, and especially the importance of winds in Compass modeling for binary black hole predictions. Sangeet Paul, Gino Carrillo, and Jackson Godfrey are three other grad students in my group, all working on population analyses with LIGO and various other things that I'll also highlight in passing. I've had a great group of undergrad students come through my group, as well as the good fortune of working with a high school teacher through a program that's local to the Pacific Northwest. There's actually some decent amount of money that can go to supporting a high school teacher to spend time in your research group for 2 consecutive summers. And so it's been really fun working with John and getting him doing some actual gravitational wave astronomy, which is really fun. Zohair Doctor, I already mentioned. He's now a research assistant professor at Northwestern in Vicky's group, my former home. And Rachel Herr has also gone to another one of my former stomping grounds at UChicago as a PhD student there now. She was an undergrad in my group. This would especially be useful toward the beginning of my visit, but we have 5 more hours of me being on campus. And so if any of these other projects happen to trigger your curiosity, these are things I'm not going to get to go into depth today to talk about, but you should track me down and talk to me if any of these things trigger your curiosity. One of them is related to modeling not signal but noise in LIGO data. Working with JD, we have put together a technique based on principal component analysis to build parameterized models of common glitches or noise transients that we have in LIGO data. This is a very common and problematic type of glitch called a blip glitch that happens in LIGO data all the time, and we've built a parameterized model for it. Why that's useful is that you can use a lot of our existing tools to leverage that. So our templated approach to searches and to parameter estimation can all benefit from having these kind of deterministic parameterized models. And we can do some useful things with building up priors and things when we are able to distill these types of glitches into some parameterized representation. Gino, he's working on a bunch of gravitational wave related things, but he's also been working on a side project with me and Andrew McFadden at NYU and a couple of others in taking a more principled approach to analyzing afterglows, and specifically using some of Andrew's more physically motivated kind of surrogate models of sophisticated modeling of afterglows and putting it all together with a more rigorous statistical analysis of light curves, especially coming from Swift, but also in other bands as well. And so that's been kind of a fun project we've been working on the side. Sangeet's been working on some gravitational wave noise analyses like we already do in the collaboration, where we are trying to marginalize over our uncertainty in the behavior of the noise. In this case, not those transient glitches like I had shown before, but the overall Gaussian background. So I can talk to you about that if that triggers your interest sometime later today. And he's also been working on, Sangeet's also been working on putting together this package for clustering. A lot of what I'm going to be talking about today is kind of Bayesian analysis, but there's also a lot of interesting things we can do with more frequentist-like approaches to understanding our catalog through clustering techniques and other things. And Sangeet's been working on that, as well as he's got a problem. He's got a lot of projects going on, as well as this approach to understanding the population using a kind of interesting mathematical framework through coagulation. And so specifically trying to model multiple generations of black holes through sequential mergers. Good. And effective spins. I'll just skip over that one. Good. So everything that I'm going to be talking to you today has ultimately come from a time series. And so I just want to spend a little bit of time kind of motivating our forward modeling approaches that we use within LIGO, especially how they relate to time series. So this is not a gravitational wave strain time series like I'll be mostly talking about for the rest of the talk. This is instead from a simulated exoplanet, specifically Earth as an exoplanet. So as some other civilization may see Earth through the eyes of their telescope. And what this is reflected light as a function of time. And so each one of these peaks shows you the division of days, and over the course of a year, you see this kind of a light curve. So this is under the assumption that we can block out the host, or in this case, our sun's light, and see just the reflected intensity of light from Earth's surface over time. And so just taking 5 snapshots of 24 hours kind of spread across the year, the information packed into this light curve, with proper forward modeling techniques, actually allows you to infer the surface map of Earth itself, and specifically the reflectance map of Earth, the albedo map. And the way we do that is with forward modeling. So we wrote this package called Exocartographer to put all of these techniques together. Ultimately, what we're trying to motivate is the science case for potential future space missions. So that could be something like launching a starshade to accompany JWST, or some other future instrument with a built-in coronagraph that's capable of blocking out host starlight and make this measurement. Not resolving an exoplanet across more than 1 pixel, but being able to make sensitive photometric measurements of reflected light over time. And with these kinds of tools, we were able to recover this surface map of Earth from those 5 epochs of 24-hour observations of Earth. And if you squint, it may look a little familiar. Any guesses as to orientation of this map? Any guesses on what this bright feature is here? Asia. Ooh, so I heard Asia, I heard India. Antarctica. Yeah, so I was of the Antarctica mind, right? That ice is pretty damn bright. But I think through orientation decisions especially, what that turned out to be is the Saharan Desert. So that is a super bright feature from Earth's reflected light curves. And another very standout feature is the big dark spot from the Pacific Ocean. And so if I go back, you can see this big dark patch here of the Pacific Ocean. And obviously we're down here. So you get the gross features with a relatively modest number of measurements, all just through this technique of forward modeling. And so what we actually did was use some data-driven techniques that I'm going to be highlighting in their application to gravitational wave analyses more toward the end of this talk. But we built a parameterized model of the map of Earth, each one of these pixels being a free parameter. This is a helpix pixelization of Earth's surface. And we put in regularization through Gaussian processes, basically a prior that prefers some amount of smoothness on some scale on this map, and then orbital properties. So in this case, we were a little bit cheeky, and we put Earth's obliquity to be 90 degrees to make sure that we can see all of Earth's surface over those 5 different epochs. You can imagine if we are looking at Earth's orbit face on, and its obliquity is such that Earth's rotation axis is pointing preferentially toward us, we're never going to be able to get information about the South Pole, right? So the reason for choosing that obliquity was just to highlight what we could do under optimal conditions, and then obviously what we do is a full Bayesian analysis. So not only do we have estimates for the albedo of each one of these pixels, we also have estimates of uncertainty on the albedo for each one of those pixels. And so all of this together is just meant to highlight the power of some of these forward modeling techniques and also data-driven techniques that I'm going to be going to in applications to gravitational waves. All of this, as I've hinted, is based on Bayes' theorem. Got to give it a nice fancy animation here. This is going to show up a bunch of times. I think everybody in the room is probably familiar with this, but just in case you're not, this is a probability density over your model parameters, which I've wrapped up into theta, conditioned on some observations, some data we've collected d. And the way we compute that is by updating our previous knowledge of those parameters, our prior, with our new observations or our probability over the data that we've measured based on guesses at those model parameters theta. And then this thing down here, the evidence or marginal likelihood, this is something that's often a nuisance if you believe in your model. If you don't believe in your model and you want to compare different models, then this can come into play in doing some Bayesian comparisons across model space. Good, so gravitational waves, again, this is probably review for everybody in the room. There's a lot of gravitational wave science going on here, but the really quick picture of it, space and time, this flat sheet when there is no presence of gravity and no presence of gravitational waves going through it. Gravitational waves passing through cause this kind of plus-shaped oscillation of the space. In this case, it's a plus polarized gravitational wave passing through the screen, and we see this alternating stretching and squeezing of space-time in perpendicular directions. The way we measure that is we throw down an L-shaped detector on this space-time. Our LIGO and Virgo instruments, in the case of LIGO, each of those arms are 4 kilometers long, and we look for that stretching and squeezing of space-time, and we look for the relative change in lengths of the arms of these two detectors. And in practice, we don't actually see the arms change. We keep these cavities in lock, and we look at the error or the correction that we apply to the arm lengths in order to keep that laser in lock, and that is our measurement of the gravitational wave strain. And so we do this not with just one detector, but with many. We have 2 LIGO instruments, one in nearby Oregon in Hanford, Washington, another down in Livingston, Louisiana, surrounded by lots of logging activity, and a third detector in Italy with 3-kilometer-long arms. We also have CAGRA that is joining our observing campaign soon, hopefully. We have GEO 600 up here that's largely a prototyping instrument, but also does really important work with AstroWatch and trying to maintain a gravitational wave detector online at all times in case we are lucky enough to get, say, a galactic supernova. And we have LIGO India that should hopefully be under construction very soon that will join the LIGO fleet. Good. And I should say, there's a notable absence down here. It'd be really great to have something like NEMO come online in the Southern Hemisphere. Good. And so this is often how we look at our sensitivity of these detectors. This is the strain amplitude density as a function of frequency of each of these instruments. Lower is better, and you can see our peak sensitivity is somewhere around gravitational wave frequencies of 100 hertz or so. And really want to point out the y-axis here. So I know you've probably heard this a bunch of times. I'm going to highlight it again because it's very mind-blowing, the level of sensitivity that these instruments are capable of. This is 1 part in 10 to the 23, 1 part in 10 to the 24 type amplitude strains that we're able to measure. And so putting this into perspective is always fun. One of my often used references is it's like measuring the distance to the nearest star, Alpha Centauri, about 4 light years away, to the precision of the width of a human hair. So that's crazy. Another way I've found useful to try to wrap your head around this level of precision, 1 part in 10 to the 23, there's something like 10 to the 13 cells in the human body. So we're orders and orders of magnitude more sensitive than being able to tell a single cell is missing from a human body. But over the human population, then we get to 10 to the 23. So gravitational wave measurements that we're doing right now are comparable to being able to tell a single cell is missing from the entire human population, which is nuts. But why do we need to make this level of precision measurement to see gravitational waves. Space-time is incredibly, incredibly stiff. You need to dump a ton of energy into stretching and squeezing space-time to have amplitudes that we're able to actually measure, even with that level of precision of 1 part in 10 to the 23. So I think this was a calculation done off the cuff by Ray Weiss in a talk at some point. But you can use dimensional analysis to come up with something like a Young's modulus of space-time, which is kind of a nonsense thing, but it's kind of fun to see where it goes. So if you wanted to come up with something like a Young's modulus of space-time using C's and G's and F's, this is what you would do to get the right units. So we've got a C squared over G, and that F there for the frequency of the gravitational wave. So it's something like 10 to the 27 pascals times this frequency term. And if you plug in our optimal sensitivity somewhere around 100 hertz, you get a Young's modulus that's something like 10 to the 20 times that of steel. So space-time is incredibly stiff. You need to put in a lot of effort to stretch it, even these minimal amounts that we're looking for with the LIGO and Virgo detectors. And so what that looks like, we need to go to extreme environments to get these gravitational waves. So here is a simulation of the gravitational waves produced by the merger of 2 black holes. So here we have 2 black holes that are gravitationally bound together. They're orbiting. As they're orbiting, they're generating gravitational waves. Those gravitational waves take energy. They're getting that energy from the orbit of the system. And so as you take energy out of the orbit, you cause that orbital separation to shrink. You cause the orbital frequency to go up. And the gravitational wave strain, which is down here, reflects that. So we have at early times low frequency gravitational waves, and then as the orbit shrinks, that frequency goes up to higher and higher values until eventually you get to this plunge where the 2 black holes go into one another, their event horizons merge, and you form a final black hole, and you have that black hole ring down. And there's lots of effort here in looking at that final merger, that final part, especially carefully, the ring down, to see what kind of information we can get from that. And so that's what the signature of a binary black hole merger, and not too differently of binary neutron stars and neutron star black hole mergers looks like. And that's what we're measuring with LIGO and Virgo. Good. So this is what it looked like the first time we did it. We were incredibly fortunate that the universe delivered a very loud signal for our first one. It made our case of making claim of detection relatively easy, though obviously there are always people that push back. It was a relatively slam dunk case, I think, of a first detection. This is showing the whitened strain in Hanford and Livingston for GW 150914. Whitened being that what we do is we take our strain data, which has that power spectral density or amplitude spectral density that I showed earlier, where we have more noise at low frequencies from seismic motion around the detectors and more noise at high frequencies from shot noise, photon counting statistics, and that peak sensitivity around 100 hertz. We take our strain signal, a time domain measurement, we go to the Fourier domain, we divide by that amplitude spectral density to even out the contribution of noise from all frequencies, and then we go back to the time domain, and we end up with this picture where you can actually see the gravitational wave signal stand out by eye, which was just mind-blowing as a first detection. And not only could our principled gravitational wave models of the gravitational wave emission from binary black hole mergers reproduce this signal, which you see in red, signal agnostic or source agnostic approaches using combinations of wavelets of these kind of sine Gaussian-like packets built up in the time frequency space also recover this signal, and it looks very consistent with what we expected from GR predictions of gravitational waves from binary black hole mergers. So everything looked mighty clean and nice. And what we get out of that data, though, is not just that measurement of a signal, obviously, it's also some understanding of the source of that gravitational wave. And so this is a really nice corner plot of that first detection, showing you all of the information that we try to extract from a signal such as that one. We've got primary mass, secondary mass of the 2 black holes in the binary. We've got an angle of inclination. We've got the distance to the binary. We have right ascension and declination on the sky, spin magnitudes of the 2 black holes, orientation of the spins of the 2 black holes. Ultimately, if you assume circularization, there are 15 total degrees of freedom for a binary black hole merger. And this 15-dimensional probability density function is how we distill the information from that gravitational wave strain. And so when we put this all together, it's going to be important to remember that we don't have precise measurements of a lot of these things. Our uncertainties on masses are appreciable. Our uncertainties on spin are big. And when we want to put all of the information that we get from LIGO observations together, it's important that we bring all of this uncertainty along for the ride. And so that's going to be a topic I'll talk about a bit. So we've had released now 3 gravitational wave transient catalogs, GWTC 1, 2, and 3. Our latest is GWTC 3, which followed the end of the 3rd observing run of the LIGO and Virgo detectors. And these are showing in mass space. Well, over here, component masses. Over here, we have total mass and mass ratio. And over here, we have total mass and mass ratio. We're constantly evolving in how we like to visualize these things. But this is giving you kind of a picture of this probabilistic catalog that we're building with LIGO and Virgo observations, and all of the uncertainty coming together in how it paints our picture of the underlying astrophysical population and what we're trying to learn from it. And so we have entered solidly into our next observing run, 04, the first half that we're calling 04A. And this is showing you the cumulative number of detections / candidates as a function of observing time in days. And so the slope of this figure gives you a sense of our sensitivity. So early on in 01, we had 2 to 3 detections. 02, we got another handful. And then our sensitivity improved pretty dramatically between 02 and 03. And you can see that we accumulated lots of detections in 03A, B, and now the slope is ever so slightly more steep in 04A, showing that we've done yet another marked improvement in sensitivity going into 04. And we are getting to numbers well over 100 at this point of, I would say, confident detections, and most surely candidates coming from 04A. So not all of these are necessarily detections. This is just all of the public alerts that we sent out in 04A that haven't been retracted. Good. So in case you're curious and want to follow along, our GraceDB, if you haven't heard of it, this is our database for detections. You can go here and you can set up alerts to your cell phone if you want to get little dings. I highly encourage you to set up a useful ringtone for when you get a text message from GraceDB telling you that we've had a new gravitational wave candidate. And so I keep talking about populations. The title of the talk talked about forests. This is the forest that we need to understand. It's this probabilistic catalog of binary black hole is what I'm going to focus on observations. And this is kind of a picture of what we actually measure. So this is the marginal posterior distribution for the primary mass, the most massive black hole in each of the binaries, in the detector frame, which I highlight because we don't actually measure the what would be the source frame masses of black holes. We measure a red-shifted version of them. The effect of redshifting on gravitational waves is to shift the masses that we measure when we observe them at Earth. This is our picture of the masses of the most massive objects of all of the black holes in the catalog so far. And so this is where we're ultimately trying to extract information about the underlying astrophysical distribution, which we want to learn. That's going to be the thing that teaches us more about how these systems are formed in the first place. And so how do we go about doing that? I've already shown Bayes' theorem, and I showed and mentioned that the prior information we had about a given set of parameters going into new observations to collecting new data. We use fiducial uninformed priors when we analyze each of those individual events that I was showing before. We just pick something broad without a lot of shape to it. So think uniform distributions and isotropic distributions when we analyze each of these individual events. But what we really should be using is something that reflects the actual astrophysical population that we expect to be these sources to be coming from. We don't expect masses of black holes to necessarily be uniform. The universe likes power laws. Maybe they're going to be more power law-like. We can think of different populations that we may want to compare against the catalog, compare against the data. And so what we ultimately want to do is replace that kind of uninformed guess going into our single event analyses with something maybe parameterized, where I'm reflecting the population level parameters in this lambda thing. And we want to infer those from the data. And so that's our goal. So here's Bayes' theorem, as I showed before, just ignoring that denominator normalization for now. What we are putting into our probabilistic catalog are these single event posteriors, where we use that kind of fiducial prior over here. And we have posterior distributions for each event in our catalog that we want to put together. And now what we're proposing is replacing that prior with now a parameterized guess at the astrophysical population, and we want to turn the crank on figuring out what those parameters are from the population based on the catalogs that we've measured. But how do we do that? What's the right likelihood? It is related to lots of things that we actually encounter in our day-to-day lives. Say the splotches of gum on sidewalk blocks or stars in the sky. It's a counting problem. So it's a Poisson process, but it's specifically an inhomogeneous Poisson point process. We don't expect the Poisson rate as a function of our parameters of interest, say primary mass of black holes or spin orientation of black holes, to be uniform in those. We expect that to evolve, and it's exactly that evolution of the rate in these parameters that is going to give us the most information about where these binaries are being formed in the first place. And so this is just a quick illustration of some of the many proposed channels for where our binary black hole detections are coming from. Largely separate them into isolated evolution over here, basically stars born gravitationally bound at birth and then come together to orbital separations tight enough by the time black holes are formed that gravitational radiation can take over and make them merge within a Hubble time. Dynamical assembly over here, think dense stellar environments where dynamical interactions, 3-body interactions, 4-body interactions can form binaries and tighten them again so that gravitational radiation can take over and make them merge. And then also gas assisted, so things like AGN disks where maybe gas is around. There's a common theme here of not only needing black holes to form and binaries to form, but those binaries being tight enough that gravitational radiation has a chance at making them merge in a Hubble time. So we invoked this early on as a field in the isolated evolution scenario because under normal stellar evolution, we often think of giant phases and things totally destroying binaries if they are born initially tight enough that when they go to black holes, they would be able to merge from a Hubble time. So in the isolated evolution channel, for example, the trick is to form binaries that are wide enough that they can undergo normal stellar evolution in giant phases and things and have the binary survive, but at some point in that evolution, tighten it sufficiently that gravitational radiation can take over at late times and merge them. And so you see things like, let's see, we have common envelope evolution, so that it shows up down here. So there you actually have a compact object form, and then later on it will spend some time inside of the outer envelope of its companion star, and dynamical friction will dramatically shrink that orbit. And the same thing goes for gas-assisted formation channels like AGN disks. All that gas around can help to shrink orbital separations pretty quickly. And then the other way to get around this is dynamical assembly, is that you have constant interactions in a dense stellar environment that can form and tighten binaries on quick timescales. So all of these different channels have a chance at describing the population of black holes that we're detecting. And it's the goal of our population analyses, of our probabilistic fits to these probabilistic catalogs, to start to disentangle these and try to constrain the physics within these channels, to try to rule out some channels if we can. And so that's the goal. That's the ultimate goal. So just to highlight, though, the uncertainty involved on both sides. So I've already talked a lot about the uncertainty in the observations. There's also lots of uncertainty, obviously, in the formation physics and the predictions from these different channels. And just to highlight one that I've been working with, COMPASS. So this is a population synthesis code meant to encode in efficient ways as many of the physical processes as we can that we think are important for forming binaries in an isolated scenario. And so this is just, it's been a fun exploration getting kind of up and running with COMPASS and understanding everything that's gone into it. This is just one of the files, so this is .h here is a header file for the students in the room that haven't worked with compiled languages before. This is C++, and it's a compiled language. It's really fast. But anyways, this is encoding a lot of the possible assumptions that go into all of the physics that we think is important. This is over 6,000 lines of code just encoding all of these different decisions. There's things related to common envelope guesses that we have, loads and loads of stuff. So it's not really feasible to take these really rigorous simulation tools like COMPASS, like the n-body codes for globular cluster evolution, et cetera, and let them loose directly on the catalog. What we've been doing as a field is the theory side has been producing lots and lots of predictions, doing some comparisons to the gross features that we uncover from the catalog, But separately, we analyze the catalog with much simpler approaches to understanding the population, try to pull out some key features and characteristics that are starting to pop out from our probabilistic catalog, and then we try to compare these things. So what I'm kind of focused on is a little bit of that interface and trying to do our best job at extracting all of the information that's available in the catalog to better kind of highlight these features, to find new features that might be present in the data, to then take to the theory side and look for predictions that are consistent with those. And that's largely what the population group here is also working on. There's a lot of population analyses going on here. I'll talk a little bit about all of these different approaches here in a second. But just to paint a little bit the kind of picture in two different channels of what 150914, that first detection, might have looked like. So over here is a possible path in that kind of isolated formation scenario where you have two stars that are born zero-age main sequence stars bound at birth, and then they undergo lots of stellar evolution. So over here is the time scale in mega years. We have orbital separation over here in solar radii. And so you can get a sense of the scales at play here. So we have about 2,500 solar radii separation at birth. And then by the time we get down to two black holes, it's down to 47, 48 solar radii. So that's giving you a sense of that dynamical range that we need to get from separation at birth to separation at compact object formation to have gravitational waves take over. And so here is that elusive phase that I had mentioned earlier, a common envelope phase. This is one possible way to get that quick tightening of the orbit. Over here are a few possible paths in a globular cluster for forming something like 150914. So all of these tiny little blue and red circles are representing different dynamical interactions in that dense stellar environment. So there's like binary single scattering, binary scattering, binary single exchange, binary exchange, and then three-body binary formation. So all kinds of interactions going on from the time where black holes are formed to the time where a binary is formed that's tight enough to have gravitational wave radiation take over and merge that binary. So really messy processes kind of under the hood in a lot of these formation predictions. And so just to highlight that the importance of that inhomogeneous part of the Poisson process. So each one of these different formation channels, under certain assumptions, you can make a prediction for what you would expect the rate of detections to be. And that's something that we obviously know very well. We know how many events are going into our catalog, so we can make clear statements about the overall rate of mergers, let's say as a function, let's say for simplicity, just the local merger rate, so the number of binaries formed, or mergers that happen per cubic gigaparsec. This is showing the prediction of rates from a bunch of different formation channels. So the x-axis in each one of these is a merger rate, so per cubic gigaparsec per year. Over here, this is representing predictions for binary neutron star mergers. Here is neutron star black hole mergers, and here are binary black hole mergers. And so this is a paper led by Ilya, by the way. And this is just painting the kind of vast landscape of theory that's at play here in predicting these catalogs. And there are wide ranges of predicted rates from each one of these channels, and they are, for the most part, very consistent with one another over wide ranges of physics, right? So here we have isolated binary evolution, just to focus on the binary black hole mergers. We've got chemically homogeneous evolution. This is where stars are formed, massive stars are formed really close together, and tidal interactions can serve to keep mixing up the star so that the core constantly has fresh hydrogen to burn, and you can kind of avoid some of those really dramatic giant phases that destroy binaries that are born tight together initially. Here we've got population 3 stars, triples, globular clusters, nuclear star clusters, young and open star clusters. So the theory landscape is really vast, and it's a little bit daunting to think about trying to put constraints on this, but that's ultimately our goal. But again, highlighting the inhomogeneous part. It's not only the rate that we need to be able to compare to from theory to observation, it's also that distribution of events across our parameter space. So the distribution of masses of black holes, the distribution of spins. And that's what we're ultimately after. So it's been a bit of a long road to get there. We made our first population constraints, our first constraints on binaries in a kind of global catalog way at the end of 01. So if memory serves me, this was Ilya pushing really hard for us to do this. So at the end of 01, we had 2 to maybe 3 binary mergers, and you've got 2 to 3 points, what do? You draw a line through them in log-log space, right? So we fit a power law distribution to the black hole population at the end of the first observing run, and we made our first constraint on a population level, and that was a measurement on a power law index describing the mass distribution of black holes. So that was pretty exciting, and that was when that kind of led off all of the things to follow. So GWTC1, after the end of '02, we started to fit some more sophisticated models to the data. So now we not only have a power law, we can truncate it and maybe even add a peak to it. And so this kind of curvy guy right here is a power law plus a potential peak described by a Gaussian that we fit to the data. And if memory serves me, the model comparisons between these, it was inconclusive that we needed a peak on top of a power law to describe the population that we were seeing in GWTC1, but this was the first hints that we saw of this possible departure from power law-like behavior in the mass distribution, which was also pretty exciting. And we also started to fit the distribution of mass ratio of binaries in the catalog. On to GWTC2. This was a paper led by your very own Eric. This is a picture of the different parameterized models we let loose on the data. So here we had our truncated power law. We also fit a broken power law. Here again is that power law plus peak. And then here is power law plus 2 peaks. So not only looking for this bump that started to show itself with GWTC1, but also possibly looking for another bump in the data as our catalog grew and grew. Here was our constraint on spin magnitudes of black holes. So this relativistic quantity between 0 and 1. Here on the cosine of the misalignment of black hole spin with the orbital angular momentum. That's a particularly interesting quantity if you're trying to separate out these different channels. So especially thinking about dynamical assembly. In isolated formation, there are lots of physics at play that can preferentially line up the spins of the stars with the orbit. In dynamical assembly, there should be no preference for the alignment of those spins, and we expect the misalignment of spin and orbital angular momentum in these binaries to be isotropic, right? So this is a particularly useful quantity if we want to start making kind of broad stroke statements about formation environments for these. And so this is the kind of picture that we had at GWTC at the end of the third O3A with GWTC2. And this, for example, this peak is now required in our understanding of the catalog. This peak at around 35 solar masses is a really dominant feature. The possibility of a second peak was actually starting to be at play here, but it turns out that the way that we allowed those peaks to kind of move around parameter space, that second peak couldn't quite go down to low enough masses to describe where we think there's another peak now in the data. And then finally, we also start to constrain the merger rate as a function of redshift. And this is also interesting because as we probe to deeper and deeper redshifts, we expect the merger rate to follow star formation rate, possibly with some lag time. And so looking for evidence of this evolution of the merger rate is something that we're really eager to do, and we're finally able to start doing now. Good. And so now what I want to highlight is a slight departure, a different approach to understanding the catalog from these kind of highly parameterized approaches that I've been describing. So power laws, Gaussian peaks on top of power laws, and start thinking about kind of where we're going. So you saw that kind of more and more vertical line of cumulative detections as we're now getting into '04, looking ahead to '05, kind of design sensitivity of A+, the kind of final iteration we are imagining so far of the LIGOs, of especially next generation telescopes like Cosmic Explorer and Einstein Telescope. The fidelity that we will be able to constrain the astrophysical population to is going to be going up and up and up. And so this kind of incremental approach to parameterized models to uncover all of the features in the parameter space is going to be becoming less and less tractable as our catalogs get bigger and bigger. I think it's still going to be super critical that we have both of the approaches that I'm going to be talking about to understand the catalog. But we want to make sure that we have some kind of eyes wide open analyses of the catalog that are able to pick out features that we may not have necessarily guessed were there and been looking for deliberately with the parameterized models. And so that's where we start to look at non-parametric models. This is a term often used to describe the techniques that I'll be talking about. Also, you'll see semi-parametric used to describe them sometimes. I think they're more very parametric. There's just loads of parameters in these models that need to be constrained. And so to avoid all of that, I'll just talk about them as data-driven. But largely, these are very flexible models that we use with the hope of uncovering all of the features in the catalog and not leaving anything on the cutting room floor by not having a parameterized approach to look for them. And so one of the techniques that my group really uses a lot are splines. And so in case you haven't seen splines before, it's basically an interpolant. It's meant to be a smooth interpolator between control points or knots. And so that's what I'm illustrating here with this one-dimensional spline. So you've got some axis here, your x dimension, that you want to plug in a value to into your model and get a guess at the value, the output of this function. And that's what the cubic spline, in this case, is doing for us. It's basically an interpolation, but we can use these knots as parameters that we can constrain in a Bayesian analysis to describe an underlying population. So here is a spline at play in a regression context. So now we've got all of this data, and we want to fit some smooth function to this data that we've observed. We can use splines, and we can do an MCMC to infer the position of all of these knots, of these control points. And this is what that kind of MCMC would look like. So every step of the MCMC, you make new guesses at the location of these knots. You get new sets of residuals, and you put all of those residuals together with a likelihood to get the probability of observing the data you observed based on your guesses at the positions of all of those control points. And so what that looks like in a gravitational wave context is we are, for example, using a cubic spline to describe the underlying astrophysical distribution of primary masses of black holes in these binaries. Each step of the MCMC, we make new guesses at the control point locations. And so every step of the MCMC, we have a new proposed population description. We turn the crank, we get loads and loads and loads of guesses at this underlying population. We get this big mess of spaghetti, and we slap down some confidence intervals or some credible intervals that highlight that kind of central 90% at every mass. And this is the type of band that we show in our population analyses, showing our guess at the underlying population of, in this case, primary masses of black holes. And so there's loads of things at play here. Obviously, data-driven techniques are very easy to be overfit. And so that's often a question that comes up, especially splines. People are very used to seeing splines in these contexts, kind of having this very characteristic kind of wavy behavior where you see tightness where you put your control points along the x-axis, right? And then you see uncertainties kind of blow up in between those control points. What we often are using are actually called p-splines or penalty splines. And so we kind of marginalize over some of these decisions of like how many knots we should be using and what the kind of uncertainty on those knots should be, our prior information on those knots should be. And we put in this kind of penalty term or effectively a prior that prefers smoothness, and that kind of helps to avoid some of the oversmoothing. So if you have questions about that, don't hesitate to ask me. I'd love to go into more details, but that's a common question that comes up. So penalty splines, but I can be happy to go into more detail. So we use these splines in a couple of different ways. One way is to modulate one of these parametric descriptions that I've been talking about kind of under the hood. So let's say you want to, you think that power law is actually a decent first guess at the underlying mass distribution of black holes. You want to fit it with a power law, but you expect there to be some deviations like this peak at 35 solar masses away from that power law. So you can use a spline to modulate that kind of underlying simplistic description of the catalog. And so that was what we did at first, was we modulated a power law. And we get those kinds of constraints that we saw from like a power law plus peak model, but we also saw some other peaks pop up. And so this is that other peak I was kind of hinting at earlier at 10 solar masses that we didn't see with that multi-peak analysis because of prior choices. And so this has a lot of nice features. One is that your kind of simple description of the underlying population is a nested model within your kind of data-driven approach. So you can do things like assess the probability of departure from that more simple description, which is nice. But it's still flexible, right? It's still able to deviate from that simpler description if the data demand it, which is what we're looking for. We've let these loose on GWTC3 along with a couple of other data-driven approaches. So the power law peak is the one I just described. That's in yellow. We also have a binned Gaussian process model, which is actually very related to that initial problem that I showed with Earth as an exoplanet. So that was a binned Gaussian process like model where the bins are the free parameters, and you force some amount of smoothness with a Gaussian process prior on top of them. That's effectively that same technique applied to gravitational waves here. And then there's also Gaussian mixture models applied here as well. And all of them kind of come to the same conclusion of there being a peak at 35 solar masses, this peak at 10 solar masses. And then with GWTC3, we started to uncover these hints of maybe even a third peak at 20 or so solar masses. Good. So we've been continuing to push the envelope on this, and we've taken these data-driven descriptions beyond just the mass distribution and looking also at mass ratio, at spin magnitude, at the misalignment of spins, and also the merger rate as a function of redshift. All of this basically gearing up for, as we collect more and more events, having techniques that are able to pull out all of these features that might be popping out of the catalog. And then we can also combine these in interesting ways. So we can take these data-driven models, put them together in a mixture model of data-driven models, and then start to try to disentangle correlations in parameters. So using mixture models is basically a crude correlated model that can model correlations across dimensions, rather than doing what we're kind of working on now, which is building up two-dimensional splines, let's say, to cover mass and mass ratio space. You can use mixture models to kind of separate out populations. So you can see like separating out the 10 solar mass peak and looking at its spin distribution relative to the rest of the catalog. And so that's something we're working on. Good. And for the sake of time, I'm just going to kind of keep going on here. And I'm really highlighting the future a lot in this talk because I think that's where these data-driven approaches are really going to come to their fruition and be really useful in preparing for our next generation of science. So there's a couple of advancements kind of down the line. I've been on this team within the LSC of putting together a proposal for what to do with current facilities to kind of fill that gap between 05 and what we hope will be a cosmic explorer, kind of Einstein telescope era. And so looking at the technology we can kind of include in current generation facilities to make a marked improvement in sensitivity. The kind of default choice that we're proposing here is this A-sharp design, and there's lots of aspects of this seismic isolation that are improved, increased laser power, better squeezing. One of the important changes is improved coating on the mirrors, so moving to a crystalline coating that I could talk a little bit about, but not in depth about if you ask me questions. But in here, this yellow band is kind of our default proposal, our kind of expected sensitivity. And in comparison, this was 03 sensitivity here, and ultimately what we hope to get with A+ design here in kind of cyan. So a pretty noticeable improvement in sensitivity is possible, and we can make measurements out to horizons. Let's see, A-sharp is yellow here, redshift of 5 or 6 at the kind of peak sensitivity in total frame, in total mass of binaries. So really, I think worth pursuing, and obviously important for lots of reasons in kind of building up to the next generation of telescopes. We're going to have lots of events. This is giving you a picture of where all of these mergers are probably happening. So on the left are binary neutron star mergers. Radially is redshift. So here's redshift 0.1, here's redshift 1, here's redshift 10. You see the peak of this kind of predicted merger rate being at the peak of star formation, somewhere around redshift 2. And then these different dashed lines are showing where our horizons are for binary neutron star mergers over here, binary black hole mergers over here. With A-sharp, which is in blue, we expect to get well past that peak of star formation. So we actually get beyond that peak and have with current generation facilities the chance of seeing the majority of binary black hole mergers in the universe, which is pretty cool. Cosmic Explorer famously will see all of the binary black hole mergers in the observable universe, so that's pretty cool. That's going to be pretty overwhelming. And then over here we have neutron star mergers. So even A-sharp doesn't quite get out to where we expect most of those mergers to be. We really need next generation facilities to get beyond the peak of merger rates in the binary neutron star part of the parameter space. But loads of detections ahead, and just a fun tweet that another Farr and I put out, kind of looking to the future. This is 16 and a half, I must have been 17 minutes of simulated Cosmic Explorer data, where we put in some astrophysically reasonable rates of mergers. And all of these are just binary mergers that stand out by eye in a spectrogram of the data. So from left to right, we've got at redshift 1, a binary neutron star merger there. Here's a binary black hole merger at a redshift 1.5. Here's another binary neutron star merger at redshift of 2. And then not shown here are the loads of low frequency, low amplitude tracks of binary neutron star mergers that are happening at the same time. So roughly we expect one binary black hole merger per 15 minutes, one binary neutron star merger per 10 minutes. And all of those are stacked on top of each other, with each of these mergers being, the binary neutron star mergers being observable in the data for up to an hour. So quite the picture of what gravitational wave astronomy looked like in our lifetimes, which is pretty exciting. So with that, I'll take the last bit I have and see if there's any questions. Thank you.
Can I ask about the rate of neutron star mergers? I mean, 1 every 15 minutes sounds good, but right now it's none since 2017.
Yeah.
So is that
That's not totally true.
Is that consistent with your expected rates? Or
Yes.
do you update them every day that it doesn't happen?
No. So far things are basically consistent. So I think as we continue to observe low numbers of detected binary neutron star mergers, that kind of very optimistic upper bound that we put on the binary neutron star merger rate kind of comes down bit by bit. But overall, this is kind of totally consistent with what we expected. Sadly, based on our constraints on binary neutron star mergers early on. So this is so far pretty consistent. That would be, I would love to make that prediction. I mean, I think it's very plausible that we'll have one or several by the end of 2004, right? I think that's about where we expect things to be.
It's about 1 a year. Current.
What's that?
It's like 1-ish per.
1-ish per year at current sensitivity. Yeah.
So that's then excluded, right? How many have you had apart from the one in 2017?
So we've had one more, 1904-25 in 2019. It didn't get as much fanfare because the localization was terrible. And so, yeah, it's 2 plus some NSBHs in there, which is also exciting. I didn't talk about those at all, but yeah, totally. So far, O4A, although not on the optimistic side, is not even on the totally pessimistic side, having not detected any binary neutron star mergers yet.
Marina?
With Cosmic Explorer and having so many different signals happening at the same time and overlapping each other, do we have the statistics worked out yet on how to separate those out from each other?
Yeah, that's a really good question. I think the Farrs are on the optimistic side, and that was kind of the point of our tweet, is that like, it sounds daunting, but you can just look at this by eye and see a lot of mergers, right? And it's not like these things are happening quickly. If you have a binary neutron star merger in band for an hour, it's like, watch a few YouTube videos, update your spectrogram. Oop, I see a track starting. Let's start winding up the analysis team. And we just watch it over the course of an hour as that thing kind of progresses through time frequency space, right? So this overlap here of this binary neutron star merger with this binary black hole merger, that's not a tough data analysis problem, right? Those two tracks are really easy to separate out. Harder are all of those kind of low frequency tracks of binary neutron stars that are down here, but I don't think it's not insurmountable. We've got some time before Cosmic Explorer comes online, so I'm not worried. I think there are things to work out, but they're not going to be that hard to work out. I think we have more than enough expertise in the community to figure it out by then.
The Smiths are optimistic, aren't they?
We're optimistic.
Yeah. There's only one Smith, but
There's a Rory Smith who does galaxies or something. You should get him on board.
we'd be the Smiths. See?
Yeah. I'm still, so with the slides,
Yeah.
how do you decide how, like, do you place them like uniformly in X?
Yeah. So what we do depends a bit on the parameter. So let's go to like. Let's go down here. Here. Good. So for mass, what we do is we place them uniformly in log mass. And what they are interpolating is the log of the rate. For, let's say, mass ratio, we do that linearly in mass ratio. We're not super sensitive to where we place the knots, largely through this kind of penalty approach that we take to smoothness. But what you really want to do is kind of pick a parameterization where things look the most spline kind of like, to have it be an easy sampling problem, right? So here, the kind of length scale that it seems to be smooth over roughly seems to be constant in log mass. And so that was kind of the motivation for picking that parameter to put the splines uniformly in. But largely, the point of the penalty is that we just crank up the number of knots to very high numbers. And so like this might have been like 60 knots or something. And so the smoothness is not driven by your knot placement, it's driven by your inference of the kind of smoothing length scale that seems to be demanded by the data.
Oh, okay. Yeah, that was my other question about how many knots.
Yeah. So we use a huge number of knots, and then we let this kind of smoothness prior take over. And so that's why we also can avoid this like sensitivity to knot placement and that bowing-like behavior that I mentioned before that we often see with spline approaches. Yeah.
Roy, yeah, just like going back to the Cosmic Explorer spectrum.
Yes.
I was curious if you know, like how loud would a binary black hole signal have to be in order to visually see things like the ring down and splendid?
Oh, that's a good question for some other people in this room. I mean, the SNRs that we're talking about here, like that screaming binary black hole merger right there, I assume that you must be able to do some precision ring down measurements with that kind of a signal. I mean, I don't even remember what the SNR of this thing was, but it was off the charts. Tegan, what do you think?
Yeah. It's I get it. That thing looks like it has an SNR of like 100 or something. So
Yeah.
you definitely should be able to. I guess even O4, there's some events in there that look like they would be pretty good for looking at the ring down. Depends what you're looking for as well though. Like higher order modes can be visible, like so like if that was like a extreme mass ratio, you might be able to just see the higher order modes tracking like sort of next to the main one, which is pretty cool. Yeah, I don't know about ring down. Sure.
Yeah, so I think there's a paper came out this year about the detecting memory signal in like next gen detectors, and they believe that they can detect it in individual events for a particularly loud event.
Still with marginalized stars.
Yeah.
Whereas the ring down SNR will still be on it.
Yeah.
Last question, Rio.
Nice question. How far can we see singularity?
Sadly, not very far. Yeah, I mean, Virgo cluster, maybe. Like, yeah.